Hi guys, in this video we're going to learn about exponential growth and decay. So first thing is an exponential function. So it's a new type of function we're going to talk about, and what makes an exponential function is the fact that your x is an exponent this time, which is why it's called exponential. So exponential functions are in this format: y equals a times b to the x, and x has to be an exponent in order for this to be an exponential function. Remember, you could rewrite this as f of x as well. So f of x equals a times b to the x. So when we look at this, a is going to be your initial value or your y-intercept, and b is going to be that growth rate. So right away, if we compare this to like y equals mx plus b, and our y-intercept is like our initial, that's going to be this a value. So this is going to be the y-intercept or the initial value. And then b is going to be your growth rate. So it's kind of opposite when we have y equals mx plus b for a line. B is actually the initial or the starting amount, and then m is the rate of change. In this case, b is going to be the rate of change, the growth or decay rate. So this is going to be the rate of change. I'm just going to write rate. So then if we look at this first example here, we have f of x equals 2 to the x. So for this one, this is really like saying f of x equals 1 times 2 to the x. We just don't write the 1 in front because 1 times anything is whatever you started with. So for this example, a is equal to 1. So your initial, your y-intercept is going to be at 1. And then the growth rate is going to be 2. So that's the b value. So first thing I want you to do is I want you to take your calculator, go ahead and enter this into the graph. So when you enter this into the graph, make sure you do caret x, and then we're going to go ahead and copy down a table. And when I copy down the table, I'm going to just pick some decimals as well as some whole numbers for this. So let's go ahead, enter it in. So I'm going to the graph. Make sure you delete anything that's already in there. So delete anything out of your graph, and then tab, enter this in. So 2 caret x. And then let's look at the table. So I'm doing this along the side with you. So if I go to Control T to see my table, if you notice the negative numbers, so the negative x values, those are decimals. So let me just go ahead and write some of those down. So negative 3 would be 0.125. Negative 2 is 0.25. Negative 1 is 0.5, 0, 1, 1, 2, 2, 4, 3, 8. And then 4, 16, but that's not going to fit on the graph, so I'll just stop there. So let's go ahead and plot these points. So I have negative 3, 0.125. That I'm just going to approximate. So it's going to be really close to 0. So negative 3 will be really close to 0. Then it's 0.25 for negative 2. Then 0.5. So it's moving a little bit closer to 1, but still pretty close to 0. 0, 1, 1, 2, 2, 4, and then 3, 8. So you start to see this curve shape, and remember 4 was going to go up to 16, so I'm just going to kind of draw that up like that, and you want it to look curved. And if you're not sure what's going to happen here, you could go back into the table and you're going to see that the graph won't actually ever cross 0. It's just going to get really, really close to 0. So what that means is this graph will never go down into the negative numbers. So what we say is that there's an asymptote at this x-axis. So remember x and y. So this line right here is an asymptote, and this line is the line y equals 0. So we call that an asymptote, meaning your graph, I know it kind of looks like it's going to cross it, It'll never actually cross that asymptote. So that's all an asymptote is. It's just a line that your graph will never go over. So there's the graph. So let's answer some questions about it. So the domain of this blue graph here, or our function 2 to the x, if you look, it's going to keep going to the left forever, and it's going to keep going to the right, because remember, domain are the x values. So the domain is going to be negative infinity to positive infinity. The range, it's never going to go down into the negatives. It's never actually going to cross this red line here. So it's never going to hit 0, y equals 0, but it'll get really, really close to 0. So that means we're going to have an open parenthesis around 0, meaning it won't cross 0, but it'll get really close to 0, all the way up to positive infinity. And then if we look, where is it increasing? So from left to right, well, it's going uphill the entire time. So it's always increasing. So from negative infinity to positive infinity. Where is it decreasing? It's never going to decrease because it's always going up. So decreasing, I would just say never decreasing. Or you could just say none. There's no interval. Something along those lines. And then where is it positive? So it's positive everywhere, meaning where the y value is positive, the y values are always positive. So it's positive from negative infinity to positive infinity. Across the entire x-axis, the graph's positive, whereas negative is going to be, there's no interval, so there's none. Or it's never negative, because it's always up in the positive y values. And then when we talked about asymptote here, I'll talk about this in a second, but we already talked about the asymptote. So it's just a line that the graph's going to get really close to, but it won't ever touch, it won't ever cross it. So in this equation, or in this example, there was an asymptote at y equals 0. So that red line that I graphed, that was your asymptote. So then the part that I skipped over up here is that this is an exponential growth function. And the reason why it's called an exponential growth function is if you look at it, it's constantly increasing. It's constantly growing. So that's why it's called an exponential growth. And right away, I looked at this and I knew it was going to be an exponential growth because this b value was a number greater than 1. So that rate was a number bigger than 1, which tells me it's growing. So the reason why this is an exponential growth function is because b is greater than 1. If it were equal to 1, then it wouldn't be doing anything. It would actually end up being a constant. It would be a straight line. So the fact that b is greater than 1 means that it's going to be a growth function. So let's look at another example. So flip the page. The next example, if you look, let's identify a and b. So again, I could rewrite this as f of x equals 1 times 0.5. I'm going to put that 0.5 in parentheses. And then to the x. So when I look at this, a is 1. So again, that y-intercept, or that starting value, is 1. And then b is 0.5. So this time b is not greater than 1. So that tells me it's not going to be a growth function right away. And like I said before, that y-intercept, that a value is 1. Let me just go back for a second on the other page. I just want to show you that just to remind you. So we said that the y-intercept was 1, or the starting value. See right here, when x equals 0, the initial y was equal to 1. So the y-intercept is 1. So that's always going to be the case. So you're going to notice that in this example as well. So let's go ahead and get some values from our calculator. So I'm going to get a table here. Make sure you clear out the other graph or delete the other graph in your calculator. And you don't need many values, so just get maybe like 4 or 5 points to plot here. So I'm going to start at -3, 8, -2, 4, -1, 2, 0, 1, and then maybe grab some decimals as well. So 1 was 0.5, 2 was 0.25, and you're going to see that these numbers start getting closer and closer to 0. So go ahead and plot these. So we have negative 3, 8, negative 2, 4, negative 1, 2, 0, 1. Again, remember there's that y-intercept because a was equal to 1, 1.5, and then 2.25, and then those numbers just got closer and closer to 0, and this started up. So make it your graph as curved as possible, and remember it shouldn't be crossing this x-axis, but it should get really, really close to it. So you kind of want to make it look like it's getting closer to it, but not actually crossing it. And then you can label your axes, label your graph. So when we look at this one, again, we see that that y-intercept, or that asymptote is at y equals 0. So here's your asymptote again, this x-axis. So your graph will never cross that, but it'll get really, really close to it. So all those decimals really close to 0 will happen, it just won't ever cross 0. So when we answer these questions about it, the domain is still going to be negative infinity to positive infinity because your graph goes to the left forever and to the right forever since it has arrows. The range will be the same as the last one. It won't ever cross 0, so it'll be from 0 to positive infinity. And when we say 0 to positive infinity, remember we put the round bracket around 0 because it's not going to actually cross 0. Where is it increasing? Well, if you look from left to right, this graph is always going downhill. So this graph is always going to be decreasing. So that means decreasing is going to be negative infinity to positive infinity, but it'll never be increasing. So the intervals where it's increasing, you can just say none. And then positive, well, this graph is still always going to be positive because it's never going to cross this asymptote. So it's always positive. So from negative infinity to positive infinity, your whole x-axis, the y values are always positive. Negative, it's never negative. So there's no intervals to state. So then this graph, because it's always decreasing, is called an exponential decay. So if you look, the difference was this b value right here. This b value was a fraction or a decimal. So, because you could have rewrote this as 1/2. So since it's a decimal, that tells me that it's decaying. It's always decreasing. So, and if you look at your y values, they're always getting smaller and smaller as you increase x. So because this function had a b value that was a fraction or a decimal, meaning that b was less than 1, but it's always going to be greater than 0. We're not going to deal with negatives here. That tells me that we have an exponential decay function. So really this just means that b is a fraction or decimal. And if you think about what negatives would mean, negatives just tell you that there's going to be a flip going on. Because remember from our last unit, HIVO, if it's a horizontal, or if it's a negative in the inside, it's going to be a horizontal flip. If it's a negative on the outside, it'll be a vertical flip. So negatives are just telling us that the whole graph is going to be flipped either horizontally or vertically. So really we care about b either being greater than 1 or between 0 and 1, meaning it's a fraction or a decimal, and then it would be a decay. And then again, we talked about that asymptote. That asymptote was at y equals 0. So remember, asymptote is just a name for a line that your graph will never cross. It'll just get really, really close to. So let's look at just kind of summarizing what we just found out, and then we'll look at just a couple other examples. So let's go to the next page. So just a quick summary. So we talked about two different types of functions. So we have an exponential growth function, and then we talked about exponential decay in these two examples. So this is kind of like the general rules that we talked about. So an exponential growth function when you look at the graph, it's always growing. So exponential growth is going to be going uphill. So it'll get really, really close to 0, and then it'll just keep going up. Where an exponential decay function will always be going downhill, getting really, really close to 0. And remember, it should be curved like. The difference in the equations, well, exponential growth, b always has to be greater than 1, so that b value has to be greater than 1, where decay, b is going to be a fraction. Or a decimal. So exponential growth is always going to be increasing. And exponential decay will always be decreasing. Always, that looks weird, always decrease. So then we're going to look at some examples where the y-intercepts and the asymptotes are going to change, and that'll be basically if a translation occurred, so if there was a shift. So that'll be coming up shortly. So I'm not going to write anything about the y-intercepts, but remember, if it's just a standard or parent function exponential, your y-intercepts are going to be at 1, so both of these would have the same y-intercepts. That asymptote was at y equals 0. But that can change, so that's why I'm not going to write that here. The growth rate, though, b being greater than 1 or b being a fraction, that's always going to remain the same. So that'll tell you if it's growth versus decay. That a value will always be that initial value, but like I said, that can change depending on if there's a translation or not. So before we start talking about translations, let's look at what if we're given an equation. So we know that the graph, you can easily tell growth means it's increasing, decay means it's decreasing. But what if you're given an equation? How do you tell? So if you look below, if I'm given these equations, I want to decide if these are growth or decay. So basically what we have to look at are these two rules right here. If b is greater than 1, it's going to be growth, and if b is a fraction or a decimal, it's going to be decay. So remember, the b value is always the value that's being raised to the exponent. So it's always next to that exponent. So in this case, it's 1.02 raised to the x. Well, yes, this is a fraction or a decimal because it's 1.02, but it's greater than 1. So let me add up here. Let me also write this, that b has to be between 0 and 1. If I say a fraction or a decimal, I mean not a number greater than 1. I mean between 0 and 1. So if I look at this one, 1.02, this is greater than 1. So that tells me that this has to be growth. Where if I look at this one, 1.50, again, greater than 1. So again, that's going to be an exponential growth function. So yes, these are decimals, but they're between, or they're greater than 1. They're not between 0 and 1. If you look at this one, 0.98. So 0.98, that's going to be a decay because that's less than 1. So that's between 0 and 1. Again, look at the number, only the number that's being raised to x. So in this case, that's going to be decay. 1.45. So this one is a number bigger than 1, so this will be growth. 0.02. This is going to be a number that's in between 0 and 1, so this will be decay. And if you look at this number that's being raised, this is equal to 1. Equal to 1 means that it's not going to be growth or decay. So this is going to be a case where it's neither. This is not even going to end up being an exponential function because what will happen is if you raise 1 to any power, it's always going to be 1. So this is really the same thing as just saying y equals 2. Because if I times 2 by 1, it's just going to be 2. So these are actually the same thing. So this would just be a horizontal line. So it would be neither decay or growth. So the last thing we're going to look at are translations of these exponential functions. So remember from our last unit, we have the acronym HIVO. So horizontal means that you're going to see a number that's in the inside. Vertical is going to be on the outside. Remember that if we're adding or subtracting numbers, so add or subtract means that you're going to be shifting or moving. So that means you're going to be moving up, down, left, or right. If you're multiplying, that means that you're going to be stretching or shrinking. And if you are multiplying by a negative, so negatives are going to tell you that there's a flip happening. Some kind of flip. So what we're going to focus on first are translations. So that means we're going to be adding or subtracting numbers. So if you look at this first one, horizontal shift, that means that it had to have happened in the inside of the function. So when we say in the inside, it really means in the exponent. Since you have an exponential function and the x is in the exponent, that means the inside is the exponent. So because this is plus 3 in the inside, so this is your HIVO, so horizontals in the inside, remember we do the opposite of what you think. So instead of thinking, okay, to the right 3, this is really going to be left 3 units. Where this one, there's a negative 3 in the inside of the function. So again, inside opposite of what you think, which means you're going to go right 3 units. So if you look at the pictures here, so here's your original, the dotted. So this is like your parent function, 2 to the x. If you look at the negative 3, it moved right 3 units. So let's just look at this y-intercept. The y-intercept moved right 3 units, where in this one with the plus 3, the y-intercept moved left 3 units. So really, the y-intercept is the easiest way to see what's happening, because remember that y-intercept is always going to be that number in front of the rate, that a value. So there's really like a 1 here. So the y-intercept starts at 1. It still has a 1 here, but because there's a shift, it moved right 3. Where this one, again, there's still a 1 in front of this 2. Like I could write this 1 times 2, same with this one. But because there's a shift, the y-intercept changed. So the old y-intercept moved left 3, which means there's a new y-intercept for these. So that's kind of what happens with those. So the next thing is going to be, what if it's a vertical shift? So if we're thinking about HIVO, well, vertical is on the outside. So that plus 3 is now on the outside of the function, meaning it's not part of the exponent. So when you do a vertical shift, it's the same as what you think. So this is the same as what you would think. So plus 3 really means you're going to go up 3. So vertical means up or down, horizontal means left or right. So for this one, when we look at our original, so here's our original. Again, look at that y-intercept. That y-intercept shifts up 3, which means, if you remember, I told you that asymptote will change. In this case, the asymptote moves up as well. So since the y-intercept is moving up 3, the asymptote, which was at 0, is also moving up 3 units. So that asymptote will always be whatever this shift is. So this is always going to tell you what the asymptote is, that number at the end. So that means this new graph will never cross this line y equals 3. So that's what's happening, since everything's getting shifted up. So those are our translations. The next thing are our shrinks or stretches, and remember that means you're multiplying by numbers. So that means you don't see adding or subtracting in the inside or the outside. You're seeing numbers being multiplied in front. So those are those a values. So instead of having a 1 in front, now you have some other numbers in front. So that a, which starts at 1 as the parent function, got multiplied by 3, where this one, the a value of 1 got multiplied by 0.5. So if we look at the dotted line, or dotted curve here, that's our parent function. Y-intercept started at 0, 1. Notice what happened. In this case, when we multiplied 1 by 3, we got 3, so the new y-intercept was at 3. Where when we multiply the y-intercept by 1/2, you get 1/2, which means that y-intercept is going to be 0.5. So basically the y-intercept got multiplied by whatever this scale factor is, or this number in front. So this one would be a vertical stretch. See how it's going, it's stretching vertically, it's getting higher. So this was a vertical stretch because that number, that a value, was bigger than 1. Where this one's going to be a vertical shrink because you multiplied by a fraction. And remember, if you think about HIVO, these numbers were on the outside, vertical, and you do what makes sense. A number bigger than 1 would get bigger. A number that's a fraction, or between 0 and 1, would be a vertical shrink because you're multiplying by something less than 1. And it's kind of hard to see the vertical stretch or vertical shrink, but really just look at like what's happening with the y-intercept. So here the y-intercept's getting higher, here it's getting closer to 0. So that's really how you can tell with those. And then if we look at just some examples with basically a combination of things, so meaning we have stretches and shifting happening. So if we look at this first example here, if I just look at the equation and try to dissect what's happening, the first thing I notice is there's a 3 in front. So the 3 in front tells me that there's going to be a vertical stretch by 3. By a factor of 3. Which means the y-intercept starts at 3, but then because there's a shift on here, it's going to end up moving. So you're going to see that the final picture, the y-intercept won't be at 3, it'll start at 3, and then it got shifted. So this tells me that the y-intercept starts at 3, because of whatever that number is, that's your y-intercept, but then shifts. So you'll see in a second once we graph it. So that's the first thing. We have this plus 1 here. So that plus 1 is going to be a horizontal movement because it's in the inside, it's in the exponent. So that tells me that I'm going to go left 1. And then the plus 5 at the end, that's on the outside. So since it's plus, it's going to be a shift. And that tells me I'm going to go up 5 because you follow what would make sense. That also tells me that my asymptote is going to be at y equals 5 because that number at the end is always going to be your asymptote if you remember that. So let's actually go through and graph it so we understand what's happening. Our basic parent function here would be y equals 2 to the x. So notice this 2 is part of the parent function. That number can change, that's that b value, but you have to have some number there. So you have to have some number other than 1 because if it's 1, then it's not going to be an exponential function. But if it's a number bigger than 1, it's going to be a growth, where if it's some kind of number between 0 and 1, it's going to be a decay. But you always have to start with something, and then you're going to do your transformations to it. So that's why when I looked at my transformations, I just looked at the 3, the plus 1, and the plus 5. I didn't look at the 2 because the 2 is really that parent function. So let's go ahead and let's just graph this final one. We don't really need to graph the parent function and then perform these things to it. Let's just put this in our calculator and graph it. So if I enter that into my calculator, I'm going to get a table, and I'm going to get some decimals, and let's get some whole numbers that'll fit. So when I enter that into the calculator, so I'm just entering this. Don't worry about doing the parent function first. I end up with, I'm going to do -3, 5.75, -2, 6.5, -1, 8, and 0, 11. So take a minute, make sure that you're getting those values. Remember when you enter this in your calculator, you do 2 caret, and then x plus 1 should all be entered as the exponent. So like your calculator will put like a little box around that. So make sure that goes in the box, and then you need to arrow out of it. So when you do the plus 5, it knows that plus 5 is not an exponent. It knows that that's at the end. So just make sure that in your calculator, only the x plus 1 is the exponent. So if you need to, pause the video, enter that in, make sure you get these numbers, and then we'll go ahead and we'll plot them. So I'm going to plot them. So negative 3, 5.75, so somewhere in here. Negative 2, 6, oops, yeah, negative 2, 6.5. Negative 1, 8, 0, 11. And remember that asymptote, I'm going to go ahead and just draw in a dotted line for that asymptote at 5, because that's going to actually help me with the graph of it. So here's my asymptote. So I know that my graph right here, it's going to eventually have to curve, and it won't ever cross y equals 5. So that asymptote's important, so you make sure that you don't actually cross this line. So I'm going to have a curve kind of something like this. And then I'm going to just make sure I label that. So there's my graph. And again, make sure it doesn't cross y equals 5, because that's your asymptote. So last thing I want to talk about is what that y-intercept. So if you started at 3, your y-intercept, which is what's happening when you multiply your parent function by 3, it would have started at 3. And then what happens is we said it's going to go left 1 and then up 5. So 1, 2, 3, 4, 5. So this point right here is where that y-intercept shifted to, which is why the y-intercept's no longer at 3, even though that value in front is 3. The y-intercept got shifted, which then gave you a new y-intercept from a different point that was shifted. So that's why the y-intercept's not at 3, even though you see the 3 in front. So that'll be it for this.